Okay, so have you ever watched like a basketball game? I mean, you see those players, right? Like weaving through defenders and making those crazy cross-court passes.
Yeah.
It's amazing.
It really is.
It's like a symphony of motion.
A symphony of motion.
And that's actually what we're diving deep into today, the physics of how it all works.
Right.
Our source material for this is a physics text.
Okay.
It's called IEC 107.pdf, and it breaks down motion.
Okay.
From like simple straight lines to, the mind-bending world of circular movement.
Yeah.
But our mission today is to really understand those core concepts, but without getting bogged down in all those.
Yeah, all the equations.
Yeah, all those complex equations and stuff.
Exactly. Yeah. So
it's interesting because, we often infer motion indirectly, right? Like if you see leaves rustling.
Oh, yeah.
You know that the wind is at play.
Right.
Even though you can't see the air itself moving.
That's so true.
It's like, I don't know if you've ever had this, but it's like when you're sitting on a train.
Uh-huh.
And you feel like you're moving.
Right.
But it's actually the train next to you.
Yeah.
That's pulling away from you.
Yeah, I've definitely felt that before.
It's all about perspective, right?
Exactly.
That's so wild.
Yeah, and our source material actually calls this the importance of reference points.
Oh, okay.
Yeah, it's all about perspective, right? Like from your seat on the bus, the trees seem to whiz by.
Yeah.
But to someone standing on the sidewalk, you're the one in motion.
Oh, wow.
So it's all relative.
So relative.
Yeah.
So that relativity is like key to grasping the difference, I think, between distance and displacement.
Absolutely.
Right.
So think of like a GPS guiding you.
Okay.
It doesn't care about like the scenic route you took with all its twists and turns. You know? It calculates the shortest path.
Right.
The displacement from point A to point B.
So distance is like your car's odometer, basically, right?
Exactly.
Just adding up the miles.
Yeah.
But displacement is like...
More strategic.
Yeah, more strategic. Yeah. So if you walk a lap around a track, you've covered a distance.
You have.
But your displacement is 0 because
Exactly,
you end up right back where you started.
You're right back where you started.
That's so interesting.
No, it's fascinating, right?
Our source uses this great visual of an object that's moving from point O to A, then back to B, and finally to C.
Right.
So, like, the distance is the whole zigzag path, but the displacement is just that straight line from O to C.
Right, that direct path.
Right.
Yeah.
And so understanding displacement then lays the foundation for understanding velocity.
Yeah.
Which isn't just speed.
Right.
Speed is just how fast you're going, right?
Right, like what your speedometer shows.
Yeah, like kilometers per hour.
Exactly, kilometers per hour.
But velocity adds direction to that. So it's like 60 kilometers per hour, but heading north.
Heading north, yeah.
Right.
Exactly.
And even on like a short trip, your speedometer needle, it rarely stays still.
It's always moving.
They're constantly speeding up, slowing down.
Right.
And our source talks about average speed.
Yeah.
Which is like the big picture.
Yeah, the overall.
Of how fast you went.
Right.
Versus instantaneous speed.
Yes.
Which is like at the snapshot.
Right now, at this moment.
Yeah, that your speedometer shows at any given moment.
Exactly.
This difference is actually crucial for understanding how speed limits work.
Yeah.
Because they're all about that instantaneous speed.
Yes. That snapshot.
Not your average speed for the whole trip.
Not the overall average.
Right.
Exactly.
Which brings us to acceleration.
Yes.
Which is often mistaken as just speeding up.
Right.
But acceleration is any change in velocity.
Any change, yeah.
So it can be speeding up.
It can be speeding up.
Slowing down.
Slowing down.
Even just changing direction.
Even changing direction at a constant speed.
Right.
It's all acceleration.
Okay, so think about it.
Okay.
You feel acceleration when you slam on your brakes.
Yes.
When you floor it.
Exactly.
And even when you, like...
Take a sharp turn.
Take a sharp turn.
Yeah.
Whoa, okay.
Yeah.
My head's spinning a little bit.
I know it's a little counterintuitive, but...
So even if I'm driving in a perfect circle at a constant speed, I'm still accelerating.
You are still accelerating.
That seems so counterintuitive.
Yeah, but think about it this way.
Okay.
Your direction is constantly changing, right?
Right.
Even if your speed isn't.
Yeah.
And since velocity includes direction, any change in direction means a change in velocity.
Right.
Which, by definition, is acceleration.
Mind blown.
Right.
So a satellite orbiting Earth at a constant speed is constantly accelerating.
It is constantly accelerating.
Because its direction is always changing.
Because its direction is always changing.
Oh.
Yeah, and it's actually that inward acceleration that keeps it from flying off into space.
Oh, wow.
Right.
That's fascinating.
But before we, dive deeper into circular motion, let's visualize motion in a different way.
All right.
Through graphs.
Ah, graphs.
Yeah.
Those can be intimidating.
They can be, but our source suggests that they're powerful tools for representing motion.
They really are.
They really are.
Okay.
Like a distance-time graph can instantly tell you if an object is moving at a constant speed or if its speed is changing.
Okay.
A straight line means constant speed.
Right.
While a curved line means the speed is changing.
Oh, so it's like a visual representation of what's happening.
Exactly, a visual representation.
Okay.
And here's where it gets really neat.
Okay.
The steeper the line on a distance-time graph, the faster the object is moving.
Oh, wow.
It's like a visual representation of speed.
That's really cool.
It is, right?
Yeah.
And with a velocity-time graph, you can actually calculate the distance traveled.
Really?
By finding the area under the curve.
Oh, wow.
It's geometry meeting physics.
Geometry meeting physics, yeah.
I know.
I'm starting to see how these graphs can really unlock a deeper understanding of motion.
They really do.
But while graphs help us visualize motion, they also reveal something that's pretty fascinating.
What's that?
An object can have constant speed and still be accelerating.
That's right.
Which takes us back to that mind-bending concept of circular motion.
It does. It's amazing, isn't it?
It is.
Yeah.
Welcome back to the deep dive. We've been unpacking all these core concepts of motion, right? From distance and velocity to that crazy idea.
It's pretty wild, yeah.
That you can be moving at a constant speed.
Right.
But still be accelerating. Exactly.
Okay, so now I was going to add another layer to that.
Yeah.
By bringing in the equations of motion.
All right, the equations.
Oh, boy, equations.
Yeah.
Time to dust off those old math skills.
Well, don't worry. We won't get too lost in the calculations.
Okay, good.
The beauty of these equations is that they give us a really concise way to describe motion.
Okay.
Especially when the acceleration is uniform.
So when it's...
Meaning it's constant.
Constant. Okay. That sounds manageable. Yeah. So what are these, magical equations?
Well, there are three main ones.
Okay.
And they all kind of play off each other.
Right.
The first one is V is U plus at full.
Okay.
It shows the relationship between the final velocity, V, the initial velocity, the acceleration, A, and the time, T.
So if I know a car starts from rest, meaning its initial velocity is 0, and it accelerates at 5 meters per second squared?
For 10 seconds, I can use this equation to find its final velocity.
Absolutely, yeah.
That's cool.
You just plug the values in.
Okay.
So V equals 0 plus 5 meters per second says A10 is going pretty fast.
That's pretty zippy.
It is, yeah.
Okay, what's next on?
Okay. The second equation is SAT plus ATOC.
Okay.
This one relates the distance traveled, which is S, to the initial velocity, U, time, T, and acceleration. A, think of it as a distance tracker.
Okay, so if I know, a ball is thrown upwards at a certain speed, and I know, the constant downward pull of gravity, I could use this equation to figure out how high the ball goes before it starts falling back down.
You got it.
Cool.
And then there's the third equation, to ATAT S.
Okay.
This one connects the distance traveled, S, to the initial velocity.
Right.
The final velocity, V, and the acceleration, A-day.
It seems like these equations are all kind of playing with the same variables.
Yeah.
It's just
the range differently.
Yeah.
Yeah. Depending on what you're trying to find out.
Right. Okay.
Yeah.
So it's like having
it is, yeah.
a physics toolkit.
Exactly. A physics toolkit.
Okay. I like that.
You choose the right tool for the job.
Right.
Yeah.
Okay. So let's put our toolkit to use.
Right.
Our source material mentions an example of a train that starts from rest and reaches a velocity of 72 kilometers per hour in 5 minutes.
Right.
Can we use our equations to figure out its acceleration,
Yeah.
how far it travels?
Absolutely. Let's break it down.
Okay.
So we know the initial velocity is 0 because it starts from rest. The final velocity is 72 kilometers per hour.
Yeah.
But we need to convert that to meters per second to keep our units consistent.
Right.
And the time is 5 minutes. which translates to 300 seconds.
Okay, so we know the initial velocity, the final velocity.
We do.
And the time.
Yeah.
And we want to find the acceleration.
Right.
Looks like it's time to pull out equation number 1.
It does.
The EU plus at.
Right on.
Okay.
Let's rearrange that equation to solve for A.
Okay.
So we get a VUAT.
Okay. Plugging in the values.
Yes.
We get a 20 meters, 0 meters, $300, 315 meter dollars is sexy.
Okay.
That's a much smaller acceleration.
It is, yeah.
Than that car we talked about earlier.
Well, remember, trains are massive.
Right.
So it takes them more time.
Yeah, it takes a while.
To get up to speed.
Yeah, to get going.
Yeah.
Okay, now, to find the distance traveled,
yes,
we can use the second equation.
We can.
SU plus SE.
Right.
And since the initial velocity is 0,
yes,
we can just simplify that too.
We can to SU, right.
Exactly.
Okay, so now we plug in the values.
Plug in the values, yep.
And we get, it's 115 meters or 500 meters, 300 raised to 3,000 meters or 3 kilometers.
3 kilometers, wow.
So that train travels 3 kilometers in just 5 minutes.
That's impressive.
All while accelerating.
And a pretty gentle pace.
Yeah.
Yeah.
That's impressive.
It is, and we figured it all out.
I know.
Using those simple equations of motion.
Right.
These equations can be applied to so many scenarios.
Yeah.
Like objects falling due to gravity or cars slamming on their brakes.
Right.
Yeah.
It's kind of empowering.
It is.
Knowing we can, predict how things move.
You can, yeah.
With these formulas.
It is. The physics gives us this incredible ability to understand and predict the world around us.
Right.
But it's important to remember that these equations work best when acceleration is uniform.
Okay.
In the real world, things are often much more complex. Right, like that car in rush hour traffic we were talking about.
Exactly.
Its acceleration is probably...
It's all over the place.
Yeah, constantly changing.
Yeah, constantly changing as it weaves through the other cars.
Right.
Exactly.
But even in those situations... These equations can still provide valuable insights. Right.
They can. You can break down complex motion into smaller segments.
Right.
Where the acceleration is roughly constant.
Okay.
And apply the equations to those segments.
So it's like solving a puzzle, right?
It is.
By understanding those fundamental components.
Yes.
To get a clear picture.
Of the bigger picture.
Yeah. Yeah.
It's a great analogy.
Okay, cool.
And as we kind of delve deeper into this topic, we'll see more of those nuances and complexities.
Right.
But for now, we've got a good grasp of these equations of motion.
Yeah, I agree. I bet our listeners are starting to see...
I hope so.
Like all these physics concepts.
I hope so.
Just playing out everywhere they look.
Everywhere.
Right.
I hope so.
But before we move on to our final thoughts...
Okay.
Let's just take a moment to reflect on everything we've covered.
Okay.
Okay, so we started by talking about...
the basic concepts of motion.
Yeah.
Yeah.
Then we looked at how graphs can help us...
to visualize motion.
Yeah. Then we explored...
the equations that govern motion.
The equation. Yeah. And now we've even considered how understanding these principles can help us make better decisions in our everyday lives.
You can, yeah.
So when we come back
for
part 3, we'll tackle some thought-provoking scenarios and see how understanding motion can help us make smarter decisions in our daily lives.
All right, looking forward to it.
Welcome back to the Deep Dive. We've been on quite a journey, right? Exploring the physics of motion.
It's been a ride.
Yeah.
From those observations we make every day, like cars and buses,
to
that mind-bending world of circular motion.
Yeah.
And even those handy equations that help us predict how objects move.
Exactly. And, physics isn't just about those abstract concepts and equations.
No, it's not.
Right. It's about understanding the world around us.
Absolutely.
And using that knowledge to kind of navigate it safely. Yeah, safely and effectively. Okay, so our source material actually has this section called Think and Act. And it really got me thinking about real life scenarios where understanding motion can be so crucial. Like imagine you're driving on a highway. And you see a car ahead of you slam on its brakes.
Oh yeah.
What happens in that split second, you know?
Well, first there's your reaction time.
Right.
It takes a fraction of a second for your brain to process that visual information.
Right.
Realize there's danger.
Yeah.
Send the signal to your foot to hit the brakes.
And during that reaction time,
yes,
your car is still moving
It is.
At its original speed, right?
Right, at that original speed.
So it's covering a certain distance.
It is covering that distance.
That's why it's so important.
It is.
To maintain a safe following distance.
Absolutely.
Especially at higher speeds.
Especially at higher speeds, yeah.
Right.
The faster you're going,
yeah,
the more distance you'll cover.
Yeah.
During that reaction time.
Okay, and then once you hit the brakes,
yeah,
your car starts to decelerate.
Decelerate, yeah.
And that rate of deceleration depends on...
It depends on a lot of things.
Okay.
The condition of your brakes.
Right.
The road surface.
Yeah.
Even the weather.
So if it's raining or snowing...
Yeah, if it's slippery...
your braking distance is going to be longer.
It will be.
Because there's less friction.
Exactly. Less friction.
Between your tires and the road?
Between those tires and the road, yeah.
Right.
And this is where understanding acceleration...
right.
And those equations of motion
yeah.
can be really helpful.
Yeah.
We can calculate how long it takes for your car to come to a complete stop.
Right.
Given its initial speed and the rate of deceleration.
That's amazing.
It is, yeah.
So physics can actually help us stay safe on the road.
Absolutely.
But understanding motion isn't just about avoiding danger.
It's not.
Right. It's also about appreciating the wonders of the natural world.
It is. You're absolutely right.
Yeah.
Our source material actually talks about how we can harness controlled motion to benefit humanity.
Okay.
One great example is hydroelectric power.
Right.
By controlling the flow of water through dams.
Yeah.
We convert the water's kinetic energy, the energy of motion, into electrical energy that powers our homes and cities.
That's incredible.
It is.
So something as basic as motion can be.
That's the powerful thing.
Yeah.
A force of nature and a tool for human ingenuity.
It's like our source says. We sometimes are endangered by the motion of objects around us, especially if that motion is erratic and uncontrolled, as observed in a flooded river, a hurricane, or a tsunami. On the other hand, controlled motion can be a service to human beings, such as in the generation of hydroelectric power.
Exactly.
Right.
Yeah, it really highlights the importance of understanding motion and how it impacts our lives in so many ways.
It makes you appreciate
It does.
the beauty of physics, right?
Yeah.
The graceful flight of birds, the mesmerizing dance of ocean waves, the swirling patterns of galaxies.
It's all physics.
Yeah.
It's all around us.
All those phenomena can be understood through the lens of physics.
It's true.
Right.
The more we understand, the more we appreciate the intricate workings of the universe.
Absolutely. We've explored so much in this deep dive.
We have.
Right?
Yeah, we started with basic concepts.
Yeah.
Then we looked at how graphs can help us visualize motion. Explored those equations that govern motion.
Right.
And even considered how understanding these principles can help us make better decisions in our daily lives.
So the next time you're like marveling at a bird in flight, or maybe even like cautiously navigating a busy intersection, just remember you're witnessing the physics of motion in action.
You are.
It's all around us.
It is.
And remember, there's always more to learn.
Absolutely.
And explore.
Always more.
Keep those questions coming.
Keep them coming.
Thanks for joining us on this episode of The Deep Dive.
It's been a pleasure.
Until next time.
Yeah.
Keep exploring the wonders of the world around you.